In this section, we now want to put together all of the knowledge that we've learned and define something called the Biot-Savart law. So the Biot-Savart law is extremely handy when we're trying to figure out the magnetic field of something. And remember how we had our differential electric fields, or DEs, and we were able to integrate the DE so that we could get the total electric field? We're kind of going to go through a similar setup where instead of calculating the total magnetic field, we're going to find a whole bunch of dBs first and then integrate that to get our total B. So the Biot-Savart law helps us set up such problems so that we can solve for the differential magnetic field element and integrate that to get the total magnetic field. So how do we define the Biot-Savart law? It gives the contribution dB to the magnetic field at a point P due to a small element of current in the direction dl. So let's first draw a diagram so that we kind of know what we're talking about. I'll draw a wire like this. And let's assume that there's a current running through that wire in this direction, and that current will be labeled with I. So some other things we want to point out here. It's going to give the contribution dB to the magnetic field at a point P. So let's just draw a point P over here. And that point P is going to be a certain distance r away from whatever intersecting point there is with that current carrying wire. So then at this point we have this section of the wire that we're looking at. First, I know that there is going to be a vector r going this way, so we'll call this r hat. So that is essentially r is a unit vector from some sort of small differential element towards P. So now we need to figure out what dl is. It's a small change in the length of the current, so it's the direction dl. So it's going to go this way. So we're going to call this dl. And we're just going to say dl is a small length element of the wire. So what else have we not labeled from here? We have dl and we have the unit vector r, and that means they're going to be at angles to one another, and we'll say that angle is theta. So using either the left hand or right hand Fleming rule, where is our cross product going to point? So if I have dl and r, then the only option is really for the cross product to point into or out of the page. So before I talk about that, I want to go through a definition of the Biot-Savart law. So the differential magnetic field dB due to the differential current element IDL, so there's a current carrying wire, so there's a current element, is defined as follows. So this is the Biot-Savart law. It says that dB is equal to mu naught over 4 pi times IDL crossed with R over R squared. So that's our Biot-Savart law, and keep in mind we have this new constant, which is defined as 4 pi times 10 to the negative 7 n over a squared, or Tesla meter over amps. This is called the permeability of free space. So if I take a look at my dl crossed with r, my dl is essentially my a crossed with my vector b. So from any of those rules, it tells me that my cross product is going to point into the page. So that means if I take a look over here, I'm going to draw an X, and that means my dB is into the page. So the convention is that you have a dot inside a circle representing a direction out of the page, and an X is going to be into the page. Alright, so we've defined what the Biot-Savart law is, and we've kind of drawn a diagram so that we know exactly where all of our vectors are. The next thing we want to do is to solve for the magnetic field. So we know dB isn't the answer we want, it's just a differential magnetic field element. We want to determine the total magnetic field. So to determine the total magnetic field, which we'll call B, all we have to do is integrate. So that means B is equal to the integral of dB, and that's equal to the Biot-Savart law. So looking at the Biot-Savart law, I know that my permeability of free space, mu naught over 4 pi, those are constants and I can take that out. I also know that I end up with IDL crossed with R over R squared. And this is called the total magnetic field from integrating the Biot-Savart law. So then the next thing we want to discuss is basically a plan of attack when we're trying to solve problems related to magnetic fields. So I'm going to present some steps. To evaluate the magnetic field. And there's in general 5 steps, but I usually tend to combine a few steps together. The goal is essentially just to find out what your dB is, and then once you have your dB, you're good to go to try and solve for B. So if I were to break it down into small steps, the first thing I would do is to pick an appropriate coordinate system. I want to pick the coordinate system that's going to make my life easier. So whether it's Cartesian, whether it's cylindrical or spherical, pick the one that you can most easily integrate. Next, we want to define an arbitrary point, A on a circuit. And we also want to define dl in terms of your coordinate parameters. And what number 2 basically means is once you've chosen your coordinate system, make sure you can represent dl in terms of different directions in your coordinate system that you've chosen. Once you have that, then you'll be able to evaluate this cross product. So dl crossed with r hat. So you're going to end up with a magnitude and a direction. The 4th step is to look for symmetry. And essentially what we're going to try and do is decompose dB if it exists only in one specific direction. So what number 4 means is something that we've looked at quite a bit already in probably the first few chapters. Remember when we had DE? When you had DE, we were able to decompose it into DEX, DEY, and DEZ for 3D coordinate systems. And the idea is that if you have certain values or components that cancel each other out, then we'll be able to determine the final direction of our vector field. So here we're doing the exact same thing. We're going to decompose our differential magnetic field element dB, and if it only exists in the x direction, for example, then that means our dB is equal to dBx, and so that simplifies our work quite a bit. And of course, once you solve for dB, you'll be able to integrate. To find your total magnetic field.